Are the first things that form in a nascent solar system? So the first thing that forms, I'm guessing, is the star, right? Or is the star forming at the? Okay, and then after that, do the planetesimals tend to form Earth-sized objects first, or super Earth-sized objects, or the large gaseous bodies, gaseous planets that we have now in the outside of the solar system first? How does this tend to emerge, or at least maybe there isn't a regular way this happens, but how did it happen in our solar system?
So in our solar system, there's a clearly defined chronology, right? Wherein it's clear that the giant planets Jupiter and Saturn, as well as Uranus and Neptune, must have formed within the first 3 or 4 million years of the sun's lifetime. Why? Because they have, yeah, right. Like they have a lot of hydrogen and helium in their atmospheres. The hydrogen and helium disk goes away in the case of our solar system in about 4 million years, right? So that immediately sets the clock for you have to form those guys far away before the nebular clock runs out. Okay, so there's debate on as to which of the giant planets is the youngest. Right? People usually point to Jupiter as the first thing that had to have formed in the solar system because it's the most massive, but that's not a settled question. But however you do it, all of that has to get done. All that planet formation has to get completed within the first 4 million years. Now, if you look at the inner solar system, right? Mercury, Venus, Earth, and Mars. The case of Mars, we also know that Mars formed pretty early, right? Something like 1 or 2 million years after the sun was born. But the Earth didn't finish its accretion until something like 60 to 90 million years after the formation of the sun. Okay, and we know that from dating the lunar, like the moon forming impact. Okay, that happened about 60 to 90 million years after the formation of the sun. Some people think it's a little bit earlier, it's maybe 30, but the point is it's tens of millions of years, not millions of years. Okay? And so that kind of gives you a sense for the chronology of the inner solar system lagging the formation of the outer solar system. Then there's the final question of, the rearrangement, right? So the solar system as it formed, did it stay the way that it looked? And the answer is no. We know now that the giant planets underwent an orbital rearrangement. Their orbits expanded by kind of a factor of 2. And that kind of chaotic expansion led to the formation of the Kuiper Belt. So the Kuiper Belt that we see today, this population of icy debris beyond Neptune, is the leftover kind of 0.1 or 0.01% of a much broader population of icy asteroids that facilitated this orbital rearrangement, then got ejected into interstellar space. So there's kind of multiple steps to the evolution of the solar system.
You said that the hydrogen and helium runs out in the first 3 or 4 million years. And is this figure similar for all stars, regardless of size, that the large gassy planets tend to form early and far away?
That's correct. Yeah. So if you just look at stars, that are a few million years old, they show signatures of accreting hydrogen and helium. Whereas if you look at stars substantially older, they don't show any evidence of having hydrogen and helium in orbit around them. So we think this is pretty generic, and the solar system kind of falls into a relatively typical timescale range from this point of view.
And then this is something I didn't catch but that maybe you said is the reason that the gassy planets tend to form far away and the rocky terrestrial planets form closer because the heavier planets or sorry, the rockier planets constituents are heavier, and just like with the Earth, the light things tend to float higher, and the heavier things like us tend to stay closer to the center of gravity. That's why the distribution is like that, the way the planets formed.
Yeah, that's not the reason, but it does have to do. That's not the mechanistic reason, but it does have to do with composition for sure. And the question you're asking is one that you could ask, reasonably at a planet formation conference. And if there's like 10 attendees, you'll get at least 12 different answers for exactly why, the outer solar system formed the way it did, why the inner solar system formed the way that it did. But the work that, I've been involved in over the last, couple of years, what we have kind of arrived at is that the compositional differences play a key role. Once you go far enough away in the solar system where ice can condense, right? So the ambient temperature of the gas is less than 170 degrees Kelvin, and you start to form ice grains, then effectively the stickiness of ice leads to bigger particles. Like you can kind of get bigger snowflakes in the outer solar system. And because of that, the forming cores of planets can accrete those particles better. Okay, so in a much more rapid way through a process called pebble accretion, which we didn't come up with. Our colleagues came up with it, but that process proceeds very rapidly far away from the sun. Conversely, what we have argued is that process doesn't work at all in the inner solar system. And instead, in the inner solar system, you have to rely on much slower pairwise collisions among rocky asteroids to build planets. And that's a slower process in the solar system. In some other planetary systems, the two could actually compete in terms of timescale, right? If you just have more mass to work with. But that's maybe getting a little bit too much into the weeds. So to kind of circle back to your question, I believe there's a mechanistic difference in how the terrestrial planets like the Earth form and how the giant planets like Jupiter and Saturn form. And that mechanistic difference plays a central role in nucleating the growth of the giants in a much shorter time scale.
Because so the planets like Mercury and Venus, they're so close to the sun that the ice doesn't form and become sticky, as you mentioned, and accrete around the heating nuclear. Okay, great. And one term that I've used a couple of times, but that I don't know too much about, is super Earths. So we don't have any in our solar system. Did we have them? What are super Earths? How do they form? And if it's different from the way that the Earth formed, and how did they then end up as regular Earths?
Yeah, so the question of whether or not the solar system hosted super Earths at some point, maybe early on, again, is an interesting question. I used to think that was a distinct possibility. I'm going to have a paper on getting rid of the nascent super Earths of the solar system. I think that might not be required at this point, to be honest. So some more recent work that we've done merely suggests that if you kind of invoke differences in the level of turbulence of protostellar clouds or protoplanetary disks, that's enough to explain the difference between the solar system and the more common systems of extrasolar super Earths. But to circle back to your original question of what they are, is they literally are just more massive versions of the Earth, right? It's as simple as that. For the few or kind of handful of planets where we have measured the densities, right? We know now that most of them fall onto a similar composition curve as the Earth itself. So super Earths are merely planets that are a few Earth masses, right? That are, in terms of size, maybe only a factor of 1.2, 1.3 bigger than the Earth itself. And that turns out to be the dominant outcome of planet formation throughout the galaxy. Okay? Like, for whatever reason, most planetary systems do not form the Earth. They don't form Jupiter and Saturn. They don't form the huge giant guys. They form objects that are a few times the mass of the Earth. And these are silicate-rich, kind of rocky worlds. Some of them retain hydrogen and helium atmospheres that are small, but small in terms of mass, but notable. And that's what the typical extrasolar planetary system looks like.
And so what role generally do collisions play in the formation process of planets early in the history of the solar system, or a solar system? So you mentioned that the moon impact was very important for dating the formation of the Earth. But were there once far more planetary bodies in our planetesimals? Well, there were certainly more planetesimals, but planets in our solar system that were.
Yeah, so perhaps the conventional way to imagine the inner solar system at the time when the hydrogen and helium gas first evaporated, right, when that first 3-4 million years, is a large number of Mars-sized embryos. So Mars, in terms of mass, is factor of 10 smaller than the Earth. And so perhaps when the gas dissipated, it was all kind of Mars-sized embryos plus a bunch of other rocks. Okay, and then over the dynamical evolution that unfolded over the following, tens of millions of years, those things collided together to grow into bigger, kind of terrestrial-sized bodies. So the role of collisions is everything. Right? Like, that's how you grow the planet.
And what happened to them then? I'm guessing that some of them are still floating around here in pieces, and then others became satellitetesimals, and were still more maybe the 20 Earth masses that got ejected from our solar system?
Well, so the stuff in the terrestrial region, right, where the Earth is, that all got accreted and became the terrestrial planets. Right? The terrestrial planets mostly is just Earth and Venus. Right? Mercury and Mars are 10 and 7% corrections to the mass budget of Earth and Venus. So most of that material got incorporated into Earth and Venus. The 20 Earth masses of stuff that got ejected was much further out. It was beyond the orbit of Neptune to start with. And it was the migration of Neptune and the instability of Jupiter, Saturn, Uranus, and Neptune that ejected that stuff. But it's kind of, that's happening much further away.